Hello everyone. In this lecture, we will discuss the convolution theorem and inverse Laplace transforms. Now recalling our last two lectures, in lecture 5, we have discussed the inverse Laplace transformation by using inspection and simply little adjustment with the formula table. And in lecture 6, we have discussed the inverse transformations by using partial fraction. Now here, this convolution technique will help you to find the inverse when the product of transforms is given in an easy way. So let us discuss. So you know the linearity property. Your linearity property is L AFT plus BGT. You can separate them out. Right, you can separate them out. Now the question is, what happens if this is a product here? What happens if it is FT into GT, a product here? Right, it is a product FT into GT. Now the question is, can it be L of FT? Can it be L of FT? If I ask you integral fx into gx, right? Integral fx into gx. Suppose your first function and second functions. Here we are using by parts. Here you are using by parts of integration, is not it? By parts. But it cannot be simply f and simply g. It cannot be. Similarly, here it cannot be. Here Laplace of f plus Laplace of g. It cannot be Laplace of g. Right? So how to overcome this? To overcome this, once we know the convolution, right? We know the convolution. Then it is L of ft convolution L of gt. Convolution L of gt. So this symbol here is your convolution, right? Convolution. So what is this convolution? Let us first study what is convolution. So now coming to the definition of convolution. Definition of convolution. Let ft and gt be two functions, two piecewise continuous functions. The convolution of f and g, denoted by ft convolution gt, or you can denote it by f convolution gt, or simply you say f convolution g, right? Is given by here ft convolution gt is equal to integral 0 to t f of u g of t minus u du. You see here in convolution, right? Your first t is replaced by your u. The second t here is replaced by t minus u, right? It is du, f of u g of t minus u du, right? Now you can evaluate it to get the outcome. If I ask you, for example, what is e to the power t convolution e to the power minus t, right? E to the power t. So you have, according to their definition, integral 0 to t, it will be e to the power minus u, the first one, e to the power minus u. In second one, it is e to the power plus t. Here, in second one, it is e to the power t minus u. T is replaced by t minus u du. Is not it? Now, base is same, so the power is added here. So it is integral 0 to t e to the power t minus 2u du. So the variable of integration here is u. So you can take e to the power t out. So the integration, it is integration of 0 to t e to the power minus 2u du. So this is equal to e to the power t, and you integrate it. It is e to the power minus 2u 0 to t. You divide by minus 2. Is not it? You divide it by minus 2. So this will be equal to e to the power minus t by 2. It is e to the power minus of 2t, and it is here minus 1. It is here e to the power plus t. So this will be equal to here e to the power t minus e to the power minus t divided by minus 2. So it will be this is minus of e to the power t, and this is plus. This is plus. It is e to the power minus t, and it is here plus e to the power t. So this is equal to e to the power t minus e to the power minus t divided by 2. So this is sine hyperbolic t, right? Sine hyperbolic t. Now coming to the properties of convolution. The properties. You have f convolution g is g convolution f. This property is called the commutative property. Similarly, it is associative. F convolution g convolution h is f convolution g convolution h, right? This property is your associative property. Similarly, it is also distributive property. F convolution g plus h. You can have f convolution g plus f convolution h. It is a distributive property. Similarly, if you have f convolution 0 is 0 convolution f is equal to here 0. Fifth, f convolution 1. It is not necessarily here f, right? And f convolution f greater than is equal to 0 is not always true. Is not always true, right? So these are the properties of the convolution. Now the convolution commutative property suggests f convolution g is g convolution f. Since in the definition of the convolution, the second function is complicated here rather than the first function. So we try to make the second function simpler in view of the commutative property. If it is asked, for example, what is the convolution of 1 convolution sine t, it is asked. 1 convolution sine t, right? So we can reverse it. It is sine t convolution 1 to make the second function simple. So this is equal to integral 0 to t. First t is replaced by u. Second t is replaced by t minus u. It is a constant. So it is like this. Now the integration here is integration of sine u is minus of cos u with the limit 0 to t. So this is equal to minus of cos t minus 1. So this is equal to 1 minus cos t. If you directly apply it also, then you will get the same thing, 1 minus cos t. So convolution operator here is here commutative, right? Now coming to some important examples of convolution. Suppose I ask one more example. I ask sine omega t convolution sine omega t, right? How to solve it? So this is equal to sine omega u, second sine omega t minus u du integral 0 to t. So you can make it 2 sine a sine b. right? So you multiply a half here, you multiply a 2 here. So this is equal to 1 by 2 integral 0 to t sine omega u into sine omega t minus omega u, omega t minus omega u du, right? 2 sine a sine b, 2 sine a sine b, 2 sine a sine b. The formula is cos a minus b minus cos a plus b. So you use it here, you use it here. So it will give you a 2 is multiplied here. So it is 1 by 2 sine integral 0 to t cos a minus b cos omega u or plus omega u 2 omega u cos a minus b minus omega t minus cos a plus b, right? Omega u cancel. It is simply omega t du. Now you integrate it. While you integrate it, the first function will give you half cos is sine 2 omega u minus omega t, and this t is constant here. Now 2 omega is divided here by 2 omega minus this cos omega t is constant here. So cos omega t is taken out. It is integration of du is a u, and the limit here is from 0 to t. You substitute the limit now. So after the substitution of limit, it will give you 1 by 2. It is sine omega t minus 2 omega t. So it is sine omega t by 2 omega minus cos omega t is constant here, and it is t minus 0. Just you add it. Just you add it. One more thing, it will be again for your 0, right? Again for your 0, sine omega t minus of minus sine omega t will come out here. Again minus of minus sine omega t will come here, because for upper limit it is sine omega t, fine. For lower limit it will be sine minus of omega t, right? So this will give you 1 by 2 sine 2 sine omega t by 2 omega minus t cos omega t. Now this 2 and 2 cancelled, and you simply add it. It will be sine omega t minus omega t cos omega t divided by 2 omega. Accordingly, so thus we get sine omega t convolution sine omega t is omega t cos omega t sine omega t minus omega t cos omega t. It is here sine omega t minus omega t cos omega t divided by 2 omega, right? 2 omega. Likewise, if I ask you what is cos omega t, convolution cos omega t, it will be sine omega t plus omega t cos omega t divided by 2 omega. Likewise, if I ask you what is sine omega t, convolution cos omega t, right? It will be here t sine omega t by 2, right? T sine omega t divided by here 2. So instead of this, suppose you have here cos at convolution cos bt, right? Here same omega is given by this. Now it is here, it is a and here it is b. Then likewise you will solve it and you will get it a sine at minus b sine bt divided by here a square minus b square. Here a is not equal to b, right? So in many inverse cases, right? While you evaluate the inverse, you will get this type of things. So if you remember it, then it will be easy to get the inverse in competitive examinations, right? And to get these outcomes, already have told you the trigonometrical formula I have told you, right? So here you will use the trigonometrical formula 2 sin a cos b, 2 cos a sin b, 2 cos a cos b, 2 sin a sin b to overcome this issue, right? Now coming to the most important theorem is our convolution theorem. Convolution theorem, right? Convolution theorem. So let f and g be two piecewise continuous functions. This is for the part of the existence of Laplace transform, and here L inverse of Fs is equal to Ft, and L inverse of Gs is equal to your Gt, right? Then what is your product of Fs into Gs, right? And you find the inverse. Now this is nothing but your Ft convolution Gt, right? So already you know the formula for the convolution. So when there is a product, so Ft is a function and Gt, Fs and Gs multiplied together, and you find the inverse, then it is individually Laplace of f, Laplace inverse of f into Laplace inverse of g convolution here. So this is the convolution formula you apply. 0 to t fu g of t minus u du, right? So now this convolution theorem is an important tool to find the inverse transformations. For example, if I ask you find the Laplace inverse of s by s square plus omega square whole square. Suppose you are asked to find this. So how to find this? You will write it L inverse of s by s square plus omega square into your 1 by s square plus omega square, right? To get a pattern here, you multiply omega here and you divide omega here, right? So now, so it is your Fs, it is your Fs, it is your Fs, and it is your Gs, and it is your Gs, right? So Fs will give you, what is your Ft? Fs will give you cos omega t, and your Gs will give you sin omega t. Now 1 by omega is there for the adjustment. Now already you know cos omega t convolution sin omega t, we get it here. Cos omega t convolution sin omega t, is not it? So you apply it here. So this is equal to 1 by omega here 0 to t cos omega u into sin omega t minus u du, and you proceed, and it will give you 1 by omega, it is t sin omega t divided by 2. So it will t sin omega t divided by 2 omega. Now if you think of this earlier technique, right? Alternatively, if you think of OR, how to solve it? You apply here partial fractions. It will give you a by L inverse of as plus b by, right, s square plus omega square plus your cs plus d by s square plus omega square whole square, right? And we have discussed it in our previous lecture 5. You can see our lecture 5, lecture 6, right? And how to find a b c d, the partial fraction technique. But it will be a lengthy approach, right? Lengthy approach here. So this convolution is an easy approach. It is an easy approach to overcome this, right? Likewise, suppose you ask suppose I ask you one more example. You find the Laplace inverse of 1 by s square plus s square whole square, say, right? S square plus s square whole square. So you can split it. How you can split it? It is Laplace inverse of 1 by s square plus s square into 1 by s square plus s square. So to get a pattern here, you multiply a here. To balance it, you divide your s square here. So now this will give you a by this, it will give you sine 80, and it will give you again, it will also give you the same sine 80, right? Sine 80. So 1 by s square. Now the convolution already you know this, already you remembered it. If it is a competitive exam, you can directly write it. Otherwise here 1 by s square, the same way, integral 0 to t sine au sine 80 minus au du. But you know the answer, you go on proceed. So it will give you 1 by s square sine omega t sine 80 minus 80 cos omega t by 2, right? So this is the answer here. This is the answer here. So you see how the convolution approach is a quite easy approach. Otherwise you apply the partial fraction as we discussed in our previous lecture 6. But it is an easy approach here. It is an easy approach here, and within a small little time you will able to get it, right? Similarly, suppose I ask you one more problem. One more example is you find the Laplace inverse of 1 by s square plus 4s plus 13 whole square, right? 13 whole square. So how to overcome it? So this is equal to here L inverse of 1 by s plus 2 whole square, then it is 4 remaining 9 plus 3 square whole square, right? Then you split it here. So this will be L inverse of 1 by s plus 2 square plus 3 square into 1 by s plus 2 square into plus 3 square. So to get a pattern here, you multiply 3 here, to make it balance, you divide 9 here, is not it? So that is equal to here 1 by 9, it is here e to the power minus t, e to the power minus 2t, because of this, right? It is sine 3t, and convolution e to the power minus 2t, again here sine 3t, is not it? So you apply the formula for the convolution here. So this will give you here 1 by 9 integral 0 to t e to the power minus 2u sine 3u into e to the power minus 2t plus 2u, t is replaced by t minus u, sine 3t minus 3u du, right? Now this, if you add the power, this 2u will be cancelled here, is not it? Now here e to the power minus 2t becomes a constant here. So 1 by 9 will be taken out, e to the power minus 2t can be taken out, integral 0 to t sine 3u into sine 3t minus 3u du. Now you see, this is nothing but, you see, it is simply sine 3u convolution sine 3u. So this is 1 by 9 e to the power minus 2t sine 3u convolution sine 3u, right? So you know the answer of this. You know the answer. It will give you 1 by 9 e to the power minus 2t sine omega t convolution sine omega t. Sine omega t means 3t it is t convolution t. Sin omega t minus omega t means 3t cos omega t divided by 2 omega, 2 into 3, is not it? So this is equal to e to the power minus 2t sin 3t minus 3t cos 3t, this is 3, divided by 6 into 9, 54, right? 54. So this is your answer, right? But if we want to solve it by the earlier technique, right? You see, the earlier technique is a complicated one, is not it? You can solve it in view of our lecture 6. Lecture 6, it will be as plus by a square plus 4s plus 13 plus your cs plus dy, again the whole square of this, right? So this will again here lengthy approach to solve it, right? So the thing is that if you remember this thing, then it is easy to get the outcome in little time for competitive examination. Now coming to one more last example. Suppose you are asked to find the Laplace inverse of, right, your s plus 2 by s square plus 4s plus your 5 whole square, say, right? You can solve it. L inverse of s plus 2 by s plus 2 whole square plus 1 whole square, isn't it? So this will be L inverse of, you split it, s plus 2 by s plus 2 whole square plus 1 into s plus 2 by s plus 2 whole square plus 1 square, right? Now here s is already replaced by s plus 2, means here shifting theorem, first shifting theorem, e to the power minus 2t, it will here sin t convolution e to the power minus 2t sin t. Now in the previous way you solve it to get the outcome. You can solve it in the previous way and the outcome, the answer will be t e to the power minus 2t sin 2t by 2, right? Sin 2t by, so if you solve it, you will get, it will be a sin t e to the power minus 2t sin t. But if you recall our lecture 5, if you recall our alternatively, you recall our lecture 5. In lecture 5, we have find the inverse, L inverse of integral s to infinity fs ds is ft by t, right? ft by t. In this way you have approached it, right? So here this problem, if you substitute here s square plus 4s is equal to 2 in the alternative, s square plus 4s is equal to z, you substitute, then it will be 2 into s plus 2 ds is equal to dt dz, right? So it will be of the form of, it will be L inverse of this will give you 1 by 2 integral of, right, here dp by p square. In that way you will get it minus of 1 by 2, and it is 1 by p square is 1 by p, right? And that way we have solved it in our lecture 5, s to infinity, right? So alternatively also we know the integration by parts also we know, right? It will be L inverse of as plus b by s square by this plus cs plus d by this whole square, right? And we get it and we discussed it in our lecture 6, right? So the same problem can be approached by different technique, right? However, this technique will give you the easy approach. and sometimes it is asked solve using convolution, then you have to solve it. So this is all about the application of convolution theorem in finding the inverse transforms. In the subsequent video, we will see how this convolution will help you to solve integral equation, right? Integral equation and convolution theorem and convolution theorem, right? How this convolution theorem will use to solve the integral equation, we'll see it in our subsequent video, right? So last 3 videos we have discussed how to find the inverse, right? So you should carefully use these techniques, and also in subsequent video we will see solution of ODE, right? ODE by Laplace transform. So here this inverse Laplace transform is important, right? So you should learn the inverse Laplace transform carefully so that we will proceed to these applications. Okay, thank you.